All right. Am I audible? Yep. Does this sound good? Yeah. Sound guy? Okay, great. All right. Thank you so much for having me. I'm extremely flattered and honored to be addressing this audience. I consider myself a little bit of an outsider, and I have really been relishing the opportunity to address this crowd because I have so much respect for the community. So this talk is called Distributed Systems Archeology. My name is Michael R. Bernstein, and I'm obsessed. Not with anything in particular, just in general. Okay? And I want you to be obsessed too, and so that's a big part of what this talk is about. I'm very excited. I like to talk a lot. I'm going to talk at you and try to get you on the bandwagon with me and get excited about the ideas that I have about the field. So this talk is called Distributed Systems Archeology, and it's a phrase that I came up with as a catchy talk title before I really put any thought into what it actually meant. But the more that I thought about it, the more that I convinced myself that it made sense, and apparently it made sense to the people at Basho too, so here we are. So if archaeology is defined as the study of human history through its artifacts, then I'm calling distributed systems archaeology an attempt to apply an artifact-driven approach to understanding the history of the field of distributed systems and its practice. So I'm going to try to tell the story of the field primarily through these artifacts, and instead of giving a talk and showing the work cited at the end, the work cited will actually drive the talk. But why? Well, when I pitched this talk, I was a developer at a startup, and that startup was growing, which is a good thing that startups like to do. Data was changing, money was coming in, and we needed to figure out how to proceed and not throw away everything that we had. We had to throw away a lot of the assumptions that we had made when we started building our system, but we couldn't just throw the system away and start over. The real world doesn't work like that. And so at that moment, I thought, wow, suddenly I'm a distributed systems programmer. But the reality of it is that I was one all the time. I just didn't think about it. And we were in that comfortable zone where you can remain blissfully ignorant about the challenges of distributed systems. So I was one all along, but now I was really feeling it. And so that's my personal story. But more generally, distributed systems are everywhere. And in addition to being everywhere, they are hard. They are challenging to reason about. I personally had a really hard time trying to figure out what was going on in this system as the scale of it grew. I had a difficult time even mentally tracing a path of execution that was going on inside of our system that was growing and getting more complex over time. Additionally, I didn't know how the tools worked or what tools even existed. And worse off, no one around me seemed to know what was going on either. You know, the people that are in charge are just the people that were there, they're not necessarily in charge because they know what they're doing. Not that I was in charge of much, but enough to be dangerous. And finally, I just couldn't seem to find the resources that I needed to put all these pieces together. I'm a very book-driven, paper-driven, information-driven person, so I need to read the origins I need to read the classics in whatever field that I'm trying to learn in order to understand it better. That's my technique, and this talk is a result of me attempting to apply that technique, as I said. So one merciful exception to the lack of resources that were available at the time that I pitched this talk was a blog post written by Jeff Hodges. We all just heard his beautiful mellifluous laugh. So it was really great when this came out because it was a giant list of shit that I needed to know that I had no idea about. I was like, oh, that, yes, I've seen that, and that, and that, and that, and I had no idea that I had seen any of those things. And it starts out with this quote: I've been thinking about the lessons distributed systems engineers learn on the job. So yeah, that's really what I was thinking about. Because there were a few hard lessons that appeared on the horizon that, to be frank, I did not want to learn. I wanted to learn them before and be prepared, not learn them as a consequence. So Hodges clearly states that new engineers will find literature, but not applicable lessons. So he provides some. You should read it and watch his talk from yesterday. It was really good. So that specific delta between the literature and the lessons is the space that I was trying to understand, and that's really what this talk is all about. So I saturated myself in the literature in order to get some clarity around what the field was all about and why it is so challenging to interact with distributed systems precisely at a time when we need them the most, right? Suddenly, we are distributed systems engineers, or in reality, we were distributed systems engineers all the time. But like I said, I just didn't know where those tools were. So in so doing, in reading and reflecting, I divided the history of distributed systems, the field, into three rough categories: the mind, the proof, and the market. Each of these categories represents a common thread that I've traced through the literature. And each of these threads contains information and wisdom that helped me understand where we started and how we got to where we are today. So let's get started with the mind. The first thread, the roots of distributed systems research and artificial intelligence. So at the time that I pitched this talk, I was obsessed with a different topic, and I happened to be spending a lot of time reading and trawling through the AI memos on the MIT CSAIL website, and I found a lot of amazing, amazing work by a wide range of people covering a wide range of topics. But what I started to read and get really excited about was a lot of work relating the mind to distributed systems, attempting to model technology on biological ideas. And so I got excited and started studying it, and I've distilled it down to the work of three people in particular: J.C.R. Licklider, Marvin Minsky, and Carl Hewitt. So yeah, these individuals are of prominent importance and represent the origins of distributed systems in artificial intelligence. And what was amazing to me about them was that they had this freedom to dream about the future, and this freedom allowed them to create something special at a time when anything seemed possible. Let's start with Licklider. This talk will do no justice to the man who is J.C.R. Licklider. His story is way too large to be told now. I'm going to tell you a tiny slice. He worked for the United States government in various capacities. He's the spiritual figurehead of the internet, one of the people responsible for popularizing the work of Vannevar Bush. He also helped create the AI lab at MIT that employed Minsky, who went on to teach Hewitt. That was some DARPA money or ARPA money that he dispensed at the time. So according to legend, Licklider was quite the eccentric, as you might have gathered from the title of this paper. I watched an interview with his son recently, which is really cool, on the occasion of him accepting some sort of award on his father's behalf. Tracy Licklider said that he'd like to do weird stuff like drink Coca-Cola for breakfast. He also did weird stuff like dream about connecting humanity with a large network of computers. And he went a little further with that and named that project the Intergalactic Computer Network, because he knew that his audience, who were a bunch of scientists that he was trying to pitch on this idea, would find it funny. So I just love that. It's just a great memorandum for members and affiliates of the Intergalactic Computer Network, 1968. 8 years earlier, he published a work called Man-Computer Symbiosis. You know, the heaviness of that is all in that name, right? What does that mean? What will be caused by the intersection of humanity and technology? There was a lot to dream about in 1960 to that regard. And he continued to think very deeply about these ideas for a long time. In 1968, he published The Computer as a Communication Device, which contains this really beautiful hand-drawn. These are actually two figures that I've put next to each other. I used a magical program called screen capture. And here's an image from that. And we see on this words like nodes, ports, message processor, graphic display. So we still use a lot of these terms. And he's clearly here using biology as an inspiration for how to model the flow of information through a network in 1968, which is really great. And so as I mentioned, Licklider helped to create Project Mac at MIT that employed people like Marvin Minsky, allowing him to publish a ton of amazing work and teach an entire generation of students. This work from 1970, the 1968 to 1969 progress report at the MIT AI lab, covers the depth of work that was going on at the time. We see computer vision, HCI, artificial intelligence, all these different things all sort of wrapped up into one. And work began to transition from the purely theoretical into the practical and back. And the primary concern was understanding how computers and humans could interact. And again, this one slide does Minsky no justice. If you don't know much about him, please read about him. You can watch some of his lectures at MIT on YouTube. He was lecturing up until, I think, 2007. And his lectures are absolutely incredible, interdisciplinary. extremely humane and well worth your time. So one of Minsky's students was Carl Hewitt, who in 1973 published a universal modular actor formalism for artificial intelligence. So this paper is notable because it defined the actor model of computation and discussed his programming language Planner. The actor model describes computation as being performed by a single kind of object known as an actor. And a few years later, in 1976, he published Viewing Control Structures as Patterns of Passing Messages. Hewitt's work, as I mentioned, is extremely important. I feel like it's an inflection point in the history of distributed systems research because it seemed to capture a zeitgeist and produce a concept that is quite formidable, very resonant. We all know about the actor model here. That's a very popular concept amongst attendees of this conference in particular. But even though it's technical, the humanity is not lost. For example, the two stated goals in the paper are modeling an intelligent person and modeling a society of experts, right? So this is not just about raw computational power or, how great the formal system was. This was still searching for human understanding. The actor model is one of the most enduring ideas produced at the MIT AI lab, and it's really an incredible work. Highly recommend it. And so to recap, the work of Licklider, Minsky, and Hewitt was inherently concerned with the distributed nature of knowledge and how technology could be used to solve a wide variety of problems with respect to human beings. And so I contend that the origins of the field of distributed systems can be found right here at the very intersection of technology and humanity. So the second section that covers the mind, the second section I call formalism. The role of the proof in the history of distributed systems research. So in parallel with the work that was going on at the AI lab, computer science is growing as a field, and the lines between mathematics and its application to technology were being teased out. As a backdrop, it's important for me to state that when I started studying this stuff, I didn't really understand how you could formalize a distributed system. I knew that there were proofs about distributed systems. I knew that there were formal systems that were supposed to represent distributed systems, but I just didn't understand that because, well, they're really complicated. And I didn't understand it. What is a computer? How do you represent that in a network and all these other things? I just didn't get it. And so part of me reading this work was really trying to understand the techniques that are applied in attempting to formally prove something that's so real world like a distributed system. It doesn't seem like a very simple and straightforward thing to write a proof about. What little I know about mathematical proofs is that you have to sort of reinvent and control the entire universe in order to make your proof. It has to be very self-contained. And I was having a difficult time making the connection with how you would do that with distributed systems. And so the work of three people in particular helped me understand that, helped me understand this technique. Edgar Dijkstra, Nancy Lynch, and Leslie Lamport's names are probably well known to everyone at this conference. And if you don't know their work, here's a little bit of an introduction. So in this section, I'm going to cover Dijkstra and Lynch's work. We're going to talk about Lamport in a little while. So to start, Dijkstra in 1965 published his Solution of a Problem in Concurrent Programming Control. Dijkstra's perhaps the most well-known name in the field. The ACM Symposium on Principles of Distributed Computing has a prize called the Dijkstra Prize that they give out to the best paper every year in distributed computing. And he is one of the strongest voices in computer science history on the importance of formalism. This thread really, in my mind, starts with him. And this paper in particular describes a mutual exclusion or mutex algorithm in one gorgeous page. It contains the problem statement, the solution, and a formal proof all in one page. It's beautiful. And it begins with this quote in 1965. To begin, consider n computers, each engaged in a process. I was like, I do that all the time. Right? So that seemed pretty valuable to me, because I'm, N. Because I don't even know how many computers I'm considering. So he's already in 65, he's proving small but important aspects of concurrent systems. And I started to see a relationship between concurrency and distributed systems here, right? Because things happening at the same time, or things capable of happening at the same time, or things capable of being interleaved, those are properties of concurrency. They sound like a lot of those things happen in distributed systems too. So that started to make a lot of sense to me. And then I came across this paper, 1974, Self-Stabilizing Systems in Spite of Distributed Control. It's also a rigorous, elegant, beautiful paper that I'm not going to pretend to fully understand. But self-stabilization is akin to the more modern idea of fault tolerance, where systems will eventually settle into an acceptable state. And this paper in particular went on to inspire a lot of computer scientists who followed, chief amongst them perhaps being Lamport and Lynch, who each went on to produce an incredible stream of impressive theoretical work. So Dijkstra's sort of the forefather of that. Moving on to perhaps, clearly actually one of the most important papers in distributed systems, actually arguably one of the most important papers in computer science history, is Nancy Lynch's et al.'s impossibility of distributed consensus with one faulty process. So the result in this paper, known as the FLP impossibility result, states that in an asynchronous network, distributed consensus was impossible. I mean, that's kind of a heavy word. Like, I think I know what impossible means. It means not possible, right? Maybe that's what it means, but really, actually, it's really not exactly what it means. We'll talk a little bit more about that. So the type of proof Dr. Lynch offered is also known as a negative result, one that proves that something is not possible, not that something else is. And it's interesting, in my mind, to consider what type of impact this type of proof has, how it's perceived, and what impact it has had on the field. And I'll discuss this a little bit more later. So at the end of this paper, which I don't believe most people make it to, there's this quote, okay? These results do not show that such problems cannot be solved in practice. Rather, they point up the need for more refined models of distributed computing. That doesn't sound impossible, right? Or to me, anyway. It technically is, because impossible has a very specific meaning in the paper, and that's the whole idea. That's how you understand the way that complex systems are formalized, by understanding that each aspect of that proof must have a highly specific, non-generalizable, you can't scooch it over a little bit to the left and call it the same thing. It's just that word, only as it is defined in that paper. You do, in fact, have to reinvent the universe as well in distributed systems proofs as you do in normal mathematical proofs. So yeah, it clicked for me. In order to reason about the formal properties of systems, assumptions have to be made, right? I had made this connection a little bit earlier when I was studying some programming language stuff, where I started to think about and learn about operational semantics and how operational semantics can be implemented into a programming language, and that implementation of that programming language might not have the exact semantics of the operational semantics that underlies it. So I see an analogy between those two things. And so to sum it up, all such theorems are based on these kinds of assumptions, all of them. And this technique is essential and is brilliant, but it's unfortunately often missed and misunderstood by practitioners. The next paper of Lynch's I'd like to talk about is from 1989. There's 100 impossibility proofs for distributed computing. So this paper is amazing because it collects 7 years' worth of work, in which there are 101 citations in the paper. There's literally 100 proofs in this paper. It's not hyperbole. I guess that was less popular in 1989. So as a side note, I stumbled upon this work because I trawled through Nancy Lynch's personal page, which is where all of you should be looking for the answers to all of your questions. Not just Lynch's page, but any researcher's page. Like, these people give a shit about their ideas and want you to understand them. So you might want to ask them in the form of visiting their www webpage thingy, okay? So anyway, what's so great about this paper is that it actually quite playfully collects, distills, and reports on the work in a field she helped to pioneer, right? So she released a result, 7 years passed, 100 people based results on her results, and she's gathering them. And in so doing, amongst the 100 proofs that she surveys, she finds that they all have only one thing in common, and that is the idea that the limitation imposed by local knowledge in a distributed system is sort of the starting point for all of these proofs. In other words, asynchronous networks and the potential for failure in other nodes makes certain assumptions impossible. By 1989, like I said, over 100 papers have been published, but the question is, what kind of impact did this have on researchers that followed Dr. Lynch and followed these 100 papers, and what kind of impact has that had on practitioners who have followed? Fast forward 13 years, and Lynch publishes Brewer's conjecture and the feasibility of consistent available partition-tolerant web services, wherein she turns Dr. Brewer's CAP conjecture into the CAP theorem by proving it with another so-called negative result. Many speakers at this conference will talk about this theorem. Lindsay Cooper did a much better job yesterday of explaining it than I can, so I'm not going to try. But what's interesting to note is by the time I read this paper, I was looking for those definitions. I had already been, now I kind of knew my stuff. I understood. You had to make these assumptions. What are these definitions? If I see words like consistent, available, and partition tolerant, I know I'm not going to look that shit up in the dictionary, okay? You need to read the paper, or else you don't understand what those words really mean. It's a specific meaning, period. End of story. You can't beat CAP because it only means one thing. It's a proof, right? That's real. That's real. You can prove things. It's real. But it doesn't mean that anytime you hear the word consistency, that people are talking about this consistency. She should have put a capital C. Like, I don't know what it is. Make up a new word. But consistency is confusing because it means something very specific. And just as the term impossible has its own specific meaning, just as all formalisms contain trade-offs between correctness and expressivity, the result of that is really easy to get confused. And it's actually a sort of sad irony that those who actually produce rigorous proofs are often those that are the most misunderstood, right? Because you have this conjecture, you turn it into a theorem, now it's CAP, which is an acronym, which is a super easy thing to make shit up about. So the proof gets divorced from the work that went into it, the why gets lost, it's a game of telephone, and that game is super boring. And not really that fun, and no one wins, and who likes a game like that, okay? So finally, the final topic is the market, and so far we've discussed philosophical and humanity-based origins of distributed systems research in the work of Licklider, Minsky, and Hewitt, and the formal origins in Dijkstra and Lynch, and now we're going to talk about the market. So as I mentioned, my job is the thing that motivated me to try to become a competent distributed systems engineer, still working on that, but I know many others here are in the same position. So it made me think, clearly there's a great commercial interest in distributed systems. The existence of this conference certainly validates that. And it made me wonder whether or not that had always been the case, right? Because the stuff that we had read up until this point was sort of theoretical. I didn't know what the connection to industry was, so I had fun looking around to see what the earliest examples of that were. I mean, there are arguments to be made about the AI work being industrial, but this is my talk, so I say it's not. So let's get started. So who was involved in industry early? Peter Bayless is number one, Leslie Lamport. This paper, SIFT, Design and Analysis of a Fault-Tolerant Computer for Aircraft Control, was written in 1978, and I discovered this paper on Lamport's page on the Microsoft research site, which is objectively in the top 5 greatest pages on the internet. That's a fact. I have a proof for it. So for example, what's so great about his page is that he annotates his own papers. He's got a sense of humor. I like this quote a lot. When it became clear that computers were going to be flying commercial aircraft, NASA began funding research to figure out how to make them reliable enough for the task. That's pretty glib, Leslie. I mean, come on. Anyway, that's amazing. I want you to stare at that sentence for a second. Okay? So SIFT was part of the NASA funding, and SIFT stands for Software Implemented Fault Tolerance. In other words, software is proving fault tolerance for hardware. It's pretty cool. And Lamport helped to theorize and prove the system's reliability even in the face of malicious, otherwise known as Byzantine faults. So software was now responsible for safely coordinating hardware that was responsible for human life. which is not ad revenue or what most of us spend our time thinking about. It's the lives of human beings, like when there's a bug. I don't know, do engines really fall out of airplanes, or does that only happen in cartoons? I don't really know, but something really bad happens, presumably. And it's not, right, you get it, not a blip in your metrics. So Lamport could have clearly been covered in the last section on formalism, as he published many works in response to Dijkstra's and is quite famous for his formal results, and I'm mentioning one here. But his impact to me has had influence in other ways. In 2003, he published this work, High-Level Specifications, Lessons from Industry, which is a collaboration with an Intel engineer he worked with to formally verify multiprocessor memory designs. Lamport has applied techniques of formal verification to a variety of industrial applications. And this is why, for me, he straddles the market, straddles the section on the market and the section on formalism. In this paper, Lamport claims that high-level specifications, such as the type that you can create with his TLA plus language, are essential to verifying industrial systems, concurrent algorithms, and more. TLA plus allows you to provide specifications in a sort of high-level proof language that are compiled into proofs. And the reason why I bring this up is that I feel in the long run, his work on TLA plus, which makes proving systems more accessible to engineers, will be one of his greatest contributions and will be of great importance, even though not that many people use it now. I know some people here who have tried to use it, and they're grinning at me a little bit evilly right now, but I've seen it being used in I've heard of it being used in the real world, like in Amazon, so I'm sure other people are using it too. And it shows that Lamport has made the connection between the theory of distributed systems and one form of its practice, right? I mean, we don't practice the same kind of computer science that he does, but it's interesting to consider what that relationship is and how it works. Okay, that's enough about Leslie Lamport. Another luminary in the field is Ken Berman. He's had quite a bit to say over the years about the mixture of commerce and research and its impact on practitioners. He's most noted for his work on virtual synchrony in the ISIS toolkit, which is a very well covered by his own bit of auto archaeology, a history of the virtual synchrony replication model. So virtual synchrony is, I guess, a framework for considering work in distributed systems. Its definition is a little bit nebulous. But Berman's flirtations with industry are storied. The ISIS toolkit powered the New York Stock Exchange for a long time, French air control systems, various other things. Fascinating stuff. In addition to all that work, he's an outspoken, reflective writer who has produced papers and participated in workshops where he really thinks about and cares about the impact of the field on practice and vice versa. He's had a lot to say about it. One famous exchange that he had with respect to the market and its impact on research is these two papers. So Cheriton and Skeen in 1993 published Understanding the Limitations of Causally and Totally Ordered Communication, wherein they basically lambasted this concept of networked ordered communication, not mentioning Berman or anyone else's work, although his work was quite involved. So what happened is he fired back, 1993 academia rap battle style, and published a response to Cheriton and Skeen's criticism of causal and totally ordered communication, where he calls them out, says that they have skin in the same game that he does. They're both trying to sell software to the stock market. He says that they gloss over his point, focus on one tiny aspect, and make a super lame point about his work. It's really interesting to read these back and forth. It's very heated. And the papers are fascinating because they remind us that researchers are living, breathing human beings who, like I said, have to survive and want to advance their ideas, right? So they're not living in a bubble. We're trying to get real work done. These two papers, the last two of Berman's I'll talk about, 2006 is How the Hidden Hand Shapes the Market for Software Reliability, and 2008's Toward a Cloud Computing Research Agenda. More than 10 years later, he's had some interesting perspectives about this interaction between money, research, and practice, specifically as it pertains to advancements in the field of distributed systems. And in these papers where he's not coming off a little bit bitter for his history, Berman urges us, his fellow researchers and practitioners, to pursue practical and thus humane solutions to the problem that actual people face, right? He sort of has a problem with 100 impossibility proofs about the same kind of system that don't tell us much more. I don't necessarily agree, but that's his take. He's had many interesting things to say, like about this impossibility idea, and additionally a lot about the blow that the applicability of transactions and database theory have had on the field of software reliability. So if you care about databases, you should probably read these papers. And so as a takeaway, Berman's main idea seems to be that we need to be aware of the impact that the market has on our work and thus our lives, both as researchers and as practitioners. All right, so to end the section on the market, I wanted to briefly touch on a phenomenon that has had a prolific impact on the theory and practice in distributed systems, publications from researchers in quote-unquote industrial settings. I'm mostly going to talk about Google here. Google's papers in particular have been crucial to the field. I spoke to several distributed systems engineers in preparing for this talk, all of whom said, if they were around at the time, that these papers were huge for them because they were facing problems, like I said, that I was, that they didn't know that they were facing. And here you have companies at scale, a scale that most people will never see, actually publishing the techniques they use to seemingly achieve the impossible. This feedback loop between large companies and academia, however, is seen by some as a mixed blessing because is that really applicable to me? Do the results that they produce, are the results that they produce the results that I am looking for? Sometimes they are, sometimes they're not, but unfortunately, it's always up to the practitioner who has no training to make that call. So I think that that's challenging. And likewise, between industry and academia and that level, things get kind of messy. And this leaves us in an awkward position of wanting to learn from our predecessors while being stung by the impedance mismatch in what we actually need. Okay. That was a lot. I have about 10 minutes left. I've covered each of the main threads that I introduced at the beginning of this talk. I've exposed, hopefully, some obvious sources of inspiration and tension in the current state of distributed systems theory and practice. And so to wrap things up, I'm going to cover two areas of pursuit that I think can help usher us forward so that 10 years from now, when we look back, we think that we've actually advanced the field and made it easier for people like me who have no experience to actually interact with, design, and program programs for distributed systems. The first one is programming languages. And so since I'm a programming language nerd, I was really excited as I read through this research to find that there were like literally hundreds of distributed programming languages that had been proposed throughout the years. A few of them are sitting in this audience right now. I briefly mentioned Planner, but there's tons of other ones. Most of them have really awesome names like Orc, which is one I learned about the other night. However, the idea that there is a distributed programming language that's not Erlang, like most people don't know about that. Okay? There are other ones. It's not only Erlang, but it's in libraries in other languages too. So I think it's time to destroy this myth. We can do better, do more. Okay? It's not about Erlang, it's just about access. So I'll briefly discuss two books that I think are directly applicable. The first one will not surprise anyone in the audience that knows me. Van Roy and Haridi's Concepts, Techniques, and Models of Computer Programming is my favorite computer book. I'm going to end right now because I just said computer book, but it's my favorite textbook for teaching computer science. I taught myself computer science from the ground up again by reading this book. I had a former life as a computer science educator, by the way, and had access to no such books as this. I had to teach Java, so it was a little bit different. But the thing about this book is that it got me to understand the connection between programming and computer science, which is no easy task, to be sure. You could ask Dijkstra, for instance, or anyone that's ever had the unfortunate pleasure to work with me. I'm not so clear on the connection between those two things. It's an important book for a lot of reasons. Chief amongst which is that it provides the reader with tiny, reasonable systems that grow over time. Add state, take state away. Add distribution, take it away. See how that impacts. So you have a tiny language for which you can reason about easily, grow it over time, see how that impacts the semantics. And you can make it click for yourself if you read this book. You could get a sense for the impedance mismatch found between theory and practice. It's in there for you. It's a giant book. It'll hurt your foot if it lands on it, but that's okay. Get an e-version or whatever you kids do these days. Finally, the last book in this section is Barella's 2013 book, Programming Distributed Computing Systems: A Foundational Approach. I wrote a lengthy blog post about this a couple months ago. I think it's a really important, really interesting book. It starts off with the assumption that understanding concurrent computation is essential to understanding distributed computation. So it takes you through the history of concurrent process calculi up to the future up to today, where there are formal systems that actually encode concepts like mobility, which is the idea that computation can move from place to place, and distribution, which is the concept that, I said them backwards, you're supposed to say distribution first. So distribution is the idea that computation can happen in different places, and mobility is the idea that computation can move between different places, like packets that flow in a network between computers is now something that could be encoded in the formalism, and then a programming language could be built on top of that and encode those concepts in the language itself so that we don't always have to feel like we're fighting against the programming language to get it to act in a way that we expect it to do. And so therefore, potentially programming distributed systems becomes more straightforward if the semantics of the languages that we use have these concepts encoded directly in them. Okay, that's programming languages. The last is humanity. The most fruitful work that we have achieved in the field of computer science is a direct result of the application of resources toward the ends of furthering and better understanding humanity, period. It is a simple fact that the longer we ignore this reality, the more it is to our peril. Things cannot be this way forever. The last two sources that I'll mention are deeply thoughtful and humane works above all. The first is Thurston's 1994 on Proof and Progress in Mathematics. William Thurston was a very famous, well-known mathematician. I came across his paper when he died, and it circulated around the internet. I wasn't really sure what to expect. I wasn't prepared, though. And I'm not going to say a whole lot about it, but it's a completely brain-breaking work of painful beauty. It will destroy you and potentially make you weep, so be prepared to have some tissues. As a short summary, though, Thurston deals with the idea that progress in mathematics is measured by proof, and he wants to know why and what impact that has, and actually whether or not that's actually the case, because it seems to be that that's how it works, but he's not so sure. Section 4, what is a proof in particular, has direct applicability to this talk. Thurston is discussing his recollection in this section of trying to understand what a proof is. So he says, mathematical knowledge and understanding were embedded in the minds and in the social fabric of the community of people thinking about a particular topic. This knowledge was supported by written documents, but the written documents were not really primary. He described papers that everyone knew that had proofs that were wrong, so they just didn't talk about them. He described about other things where people knew that these proofs existed, but they hadn't been published yet, right? So it's the intersection between humanity and proof that lets us make progress. So in other words, how our work gets used matters, community counts, and from this we can extrapolate that the more we consider humanity, the further we will go. Finally, I love this guy's last name, Papadimitriou, 1995, database meta theory asking the big queries. Andy Gross gave me this paper at the 11th hour, and it was great because I really needed it, and it fits perfectly in this spot. It hits on many of the notes I've brought up here in a much more deep and intelligent way that I'm capable of, and it discusses the impact of the definition of the field by negative proof, for example. He takes the idea of Kuhn's theory of revolutions in natural science and attempts to apply it to computer science, which is really fascinating, definitely a worthwhile read. And what I love is that his attempts to understand and contextualize the work done by researchers at various points in innovation cycles is a poignant reminder that our place in time impacts what we do and how effectively we do it. He also identifies and destroys the notion of the normative impact of describing a proof as positive or negative, which I thought was really cool, because he claims that really our proofs in computer science can only be negative, right? They can't really be positive. There's a shrinking versus growing effect. I'm probably going to mess that explanation up, so read his, it's much better. So computer science is a field in which has a unique interaction with mathematical formalisms, and his descriptions of that relationship are absolutely gorgeous. And the takeaway here is that it is essential to ask the big queries. That's how we will make progress. Okay, so some takeaways. Distributed systems has a fascinating history. There's a lot of literature. I've only surveyed a small amount of it here. There's a lot more to talk about. Humanity, formalism, and commerce have each had deep impact on the field and those who study and practice it. And each of the groups represented in this triangle has things to gain and things to lose based on how we pursue theory and practice going forward. And to end things, I'll give one recommendation to each group. Practitioners, to the best of your ability, recognize the formalisms your work is based on. Understand the details of the papers you're reading, and be careful with how you communicate these ideas to your peers. Seriously. And for academics, guide the community and strike a balance between alleviating current pain and making the future path clear. And to industrial researchers, provide complete implementation details in papers. What? What? Be generous. Be generous with your open source contributions and try to give advice directly to practitioners. I'm right here. Okay? So in conclusion, finally, for real, the future is bright. Distributed systems is an incredibly deep and rich field. Studying it has been a thrill. And in addition to a fascinating body of artifacts that are ripe for more archaeological work, the community is generous, motivated, and forward-thinking. And together we will do amazing things. Thank you very much. Thank you.
Take questions.
Anyone have any questions? Want to tell me how handsome I am?
You're going to put up slides with your notes.
Oh, yes. The question was, will I put up slides with my notes? Yeah, I'll publish the whole thing. I have a blog post form of this talk, too, that I'll publish in the next week or two. Anybody else? Anyone think I'm full of shit? Well.
No, I have a question.
Oh, you have a question. What's up?
Thanks, Mark. So, how many hours of reading did you do for this talk?
How many hours of reading did I do for this talk? I don't want. This is being recorded, so my wife will get really mad at me if she knows, probably. But hundreds. Okay. Yeah, hundreds. I basically started the day after the talk got accepted and tried to read like literally everything because I'm obsessed, and that wasn't the greatest idea. I probably should have taken it a little easy because at the end, the ideas all started to run into each other a little bit, and it took a lot of pain to tease out the ideas that I presented. But thanks. Yes? Yeah.
Which university is producing a certain degree of things. It's like, how the fuck do you even make
That's a really great question. I couldn't have paid you to ask a better question than that. The question was, how easy is it to get access to these papers? And the questioner recalls being in school, and it was easy to get access, but after they left school, it was harder, and you don't even know where to look, right? Does that sum it up? More or less? Okay, so the answer is, it's unfathomably terrible to try to access these papers. It is hurting us every single day. It's a gigantic barrier between human beings and the people and the knowledge. Like, it's just a giant wall. It sucks. I had to basically pirate a bunch of the papers in this talk. In terms of where to look, that's sort of the fun part for me. So I would find my main technique was find a paper that I like, look through the bibliography, right? See whose names come up a lot in these bibliographies and look at their work. Try to find their page and follow that whole graph around. That's how I've found some of the more obscure stuff that I used to inform this talk but didn't address as directly. So there's also some pretty good tools. You can do some cool sort by citations things. So I was wondering, like, what are the most cited papers in distributed systems research history? And so there's lots of different ways. But the basic point is that having to pay is terrible, and it made this really hard to do. That's a really good question. The question was, man, I'm going to have a little bit of a hard time restating it. So basically, as a practitioner, even if we had access to the papers, right, we wouldn't know which ones to read, and we don't have an infinite amount of time to read them. And it's challenging from the perspective of academics to consider like packaging it up in a textbook because you don't feel like it's at a point where that knowledge is well known enough to encapsulate in a, is that about right, or
maybe someone should write a textbook, but
yeah. Yeah, I mean, so I think that the questioners are really bringing up a couple interesting points. I had to do like just a lot of manual reading and printing, and I mean, first of all, actually, Twitter is like where I got a ton of information from you, from Peter Bayless, for example, and from Peter Alvaro, very generous academics who took time out of their own schedules to talk to me, let me interview them, made recommendations to me. So I guess I kind of messed this up because I didn't really encapsulate your question properly, but I feel like that there are timeless textbooks that can teach you a lot. I think that CTM, for example, if you read CTM, you would have so many tools at your disposal when attempting to digest these papers that you would much more quickly know what was applicable to you and not. So that's a big thing that practitioners don't really I didn't understand what formalism really meant. Like I said, I didn't even understand how you could do it. I didn't understand the process of simplification and definition and all that kind of stuff. So maybe the answer is that it's just way more basic even than, it's not all about distributed systems. This is a distributed systems conference, so that was the aim of this talk. But this talk could be the same about programming language theory or any other field of computer science. So, and I would recommend CTM at the end of any single one of those talks because I truly think that the way that it reveals that tension between implementation and formalism is just, it's invaluable. So I think the answer is that there's some basic texts that we all need to read. I think Varela's book is going to end up being a really important book because it just is it freezes a bunch of stuff in time, and it doesn't really make any specific claims other than here's information that you need to understand in order to reason about concurrent and distributed computation, and here's some current stuff that's happening in programming languages. But you could just read the first part of that book and learn way more than enough to have the tools to reason about these kinds of questions. Is that it?
Yeah.
All right. Thank you very much.